Today we are going to look at the introductions to chemistry of transitions element. Alright, the first part is the general physical properties of the first set of transitions element, titanium to copper. Right, now let's look at the electronic configurations of the D block elements. Now, before we come to the definitions of the transitions element, we'll need to understand that the transitions element located at this area of your periodic table. So basically in your periodic table, this is the S block, this is the P block, and this is the D block. Alright, we're going to focus on the D block elements and particularly the first row of the D block elements. Right, the first row of D block elements consists of 10 elements, which is shown in the table over here. Okay, it is scandium, which is the first one. The scandium is here and all the way to zinc. There are 10 elements here. All right, now, in order to know how to fill the electronic configurations of all these D block elements, we will need to understand the rules of filling. Right, let's revise on the rules of filling electrons. Right, electrons occupy the 4s orbital first before filling the 3d orbital. Why is it like that? Because 4s orbital having a lower energy compared to 3d. So therefore, we'll have to fill 4s first, then only 3d. Alright, but when we want to remove the electrons, the 4s electrons are also removed first in the formations of the positive ion, because once the 3d orbitals are occupied by electron, this will repel the 4s orbital to a slightly higher energy level. Now let's recap on this. Imagine initially this is 4s and this is 3d. Now we know that 4s orbital is having lower energy. So therefore, if we want to fill up electrons, we'll have to fill up 4s first, which is like this. Let's say 3 electrons is filled. 1, 2, 3. But according to the rules, as soon as the 3d orbital starts to fill up, these electrons in this orbital will start to repel this 4s orbital to a slightly higher energy level, which means this whole orbitals here will be repelled up to a slightly higher energy level. So it goes up right now. So the energy level for 4s orbital will be higher compared to 3d orbitals right now. So remember that if we want to form the positive ion, means we want to remove the electrons from the outer orbital, the 4s orbital becomes the outer orbital because it has the highest energy right now. So therefore, we'll need to remove electrons from these two orbitals. Okay, now let's take a look at the elements in the first row of the D block elements. The first element is scandium. It is having Sc as the symbol. If the proton number of scandium is 21, which means that the number of electrons of scandium is also 21. So thus the electronic configurations will look like this. Why is that like this? Because argon itself is having 1s2, 2s2, 2p6, 3p6. Alright, so this is the electronic configurations of the argon, where we have summarized in this with this symbol, which is Ar, and then we will have to fill up the 4s orbital first, which is 4s2 and then 3d1. So total here will be 21 electrons. The sequence of the 4s and 3d orbital is not important in this case. Alright, so therefore, for titanium, if it is having 22 electrons, it will be 18 here, followed by 4s2 and 3d2. Whereas for vanadium, it is having 23 electrons, so it is 4s2 and 3d3, For chromium, it is having 4s2 and 3d4. But if you look at it carefully, judging at this configuration, let's say this is your 4s orbital and this is your 3d orbital. 4s is having 2 electrons and 3d orbitals is having 4 electrons. What is going to happen is that this configuration is not stable. Okay, so in order to achieve stability, one of the electrons from the 4s will be promoted to 3d so that it becomes 4s 3d. 4s will have 1 orbital and 3d will be like this, which is having 5 singly filled electrons, which is more stable. And remember I've said as soon as the 3d orbital starts to fill, 4s orbital will be repelled to the higher energy level, so which is higher than 3d right now. Okay, so therefore the correct configurations of chromium should be 4s1 and 3d5 in order to achieve the half-field stability. Okay, whereas for manganese, you will have 4s2 here. Okay, and then 3d5. All right. Okay, so here there's 18 electron. 18 plus 7 equals to 25. Continue with that. For iron is 26, so it will be 2 and 6. For cobalt is 2, 7. Nickel is 2, 8. Alright, now when it comes to copper, supposingly it is 2 and 9 here. But again, in order to achieve the fully filled stability, 1 electron from the 4s orbital will be repelled will be promoted to the 3d orbital, and hence you're going to get 4s1 and 3d10 over here. And for zinc, it is 4s2 and 3d10. Alright, now this is the electronic configurations of the first row of the 3d orbitals. Alright, now here the important thing is that now we have to look at the definitions of the transitions matter. According to the definitions, it states that the transitions metal is one which form one or more stable ions which have incompletely filled d orbital. Now take particular note on this thing. It must form one or more stable ion, and that particular stable ion must have incompletely filled d orbitals. Okay, now let's look at the example. Now just now I've mentioned that the first row of the D block elements consists of the first 10 elements, which is this. However, scandium and zinc, although they are in the first row of the D block elements, but they don't count as the transitions metal. Let's take a look at the electronic configuration. Now, scandium is having this configuration. Now, if scandium were to form a stable ion, it needs to remove 3 electrons. I've mentioned that in order to remove the electrons, we have to first remove the electrons from the 4s based on what we have discussed just now, because 4s orbital has been repelled to the higher energy level. So when 2 electrons is removed, followed by this electron is removed, altogether you're left with just 18 electrons, which is the configurations of argon. Now, if you look at the configurations of the argon, there's no d electrons, and so it doesn't meet the definitions. Now, if you look at the definitions again, it says that in order to be called a transitions metal, it must form a stable ion. So now let's look at it. Scandium is a stable ion, and that in this scandium ions configuration, there's no d electrons at all. But according to the transitions metal, it says that it must have incompletely filled d orbital. This is the most fundamental conditions for it to be a transitions metal, but it fails to do so. Okay, so therefore it doesn't meet the definitions, and so it is not a transitions metal. All right, now let us take a look at zinc. For zinc, if zinc forming a stable ion, it is going to be zinc 2 plus, meaning we are going to remove total of 2 electrons. So therefore, it will becomes Ar. It's just left with 3d10. Okay, just left with 3d10. Now, according to the definitions again, it must have a stable ions which is incompletely filled d orbital. However, if you look at the d orbitals over here, it is a fully filled d orbital. So it doesn't meet the definitions either. Okay, so both of these are not counted as transitions metal. Okay, now let's take a look at why copper is counted as a transitions metal. Now let's see. Copper is having this configurations, which is Ar, 3d10 and 4s1. Now the most stable ions of copper is copper 2 plus. The electronic configurations of copper 2 plus will be Ar followed by 3d9. So if you look at this configurations of copper, it is counted as an incompletely filled d orbital. So therefore, copper is counted as a transitions metal. Alright, so now I hope you can differentiate between the D block elements and also transitions elements. So for D block elements, it means that it has valence electron falls in the orbital. So that is the definitions of D block elements. Whereas for transitions element, it means it forms one or more stable ion which have incompletely filled d orbital. Okay, so in past year questions, this is one of the questions where they ask you to differentiate the D block elements from transitions element. So in this part, the definitions of transitions metal is very important.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.